Sensing with Wi-Fi signals has gained considerable traction in recent years, with many potential applications. Imaging still objects with RF signals, however, is still a considerably challenging problem due to the lack of motion. In this research, we have proposed a completely different approach that enables Wi-Fi signals to image still objects. Our approach is based on the geometrical theory of diffraction and by exploiting the corresponding Keller cones. It is worth noting that this work is not based on collecting RF data to train a neural network. Consider this scene. If we are asked to represent this scene, we would probably produce something like this. In other words, we would trace the edges. Tracing the edges is a compressive yet informative representation of the scene. In this work, we introduce WiFract, which can generate high-quality images of objects via edge tracing. WiFract is based on the phenomenon of edge diffraction and exploits signatures that edges leave on the receiver grid. It can even enable Wi-Fi to read through walls, as we shall see. Now let's see how an edge point interacts with the incoming wave. When a wave is incident on an edge, a cone of outgoing rays emerges according to Keller's geometrical theory of diffraction. This interaction is not limited to visibly sharp edges but applies to a broader set of surfaces with a small enough curvature. Next, consider a receiver grid in the vicinity of the edge. Depending on the orientation of the edge and the direction of the incident ray, the edges leave different signatures on the receiver grid. We then propose to exploit these signatures for imaging the edges. Let's see how we do it. Here is an approximated expression for the received CSI signal power. We then propose the following edge-based backward ray tracing imaging kernel. More specifically, by using the corresponding conic section as the signature of an edge point, we find the edge orientation that maximizes the imaging kernel via hypothesis testing. Edges of real-life objects have local dependencies. We then next model the imaging space as a graph and propagate the information of the inferred high-confidence edges through the graph using Bayesian information propagation. Finally, we can further improve the final image by using existing image completion tools from the area of vision. Let's see some experimental results. We first consider two sample non-through-wall areas. We have three Wi-Fi transmitters. An unmanned vehicle then emulates an antenna array with a Wi-Fi receiver antenna whose CSI power measurements are then used for imaging. We next show how Wi-Fi can read with our proposed approach. Here are some sample letters and how they are imaged. We can see the ground truth image as well as our imaging result. As can be seen, our approach can image the details of the letters pretty well with only Wi-Fi signals. Here is a summary of all the imaged letters. As can be seen, the letters are imaged well with only Wi-Fi CSI measurements, showing the first demonstration of Wi-Fi reading. Next, let's consider imaging through walls. Here is a through-wall Wi-Fi imaging setting where we are interested in reading the letters behind the wall. Here are the letters behind the wall. And here is how our system imaged them with Wi-Fi. As can be seen, the proposed approach enables Wi-Fi to read through walls for the first time. See the paper for more details and results.